Chapter 1: The Overflow Test. Watch this water. If I asked you to close your eyes and hit a button the exact millisecond this glass overflows, you could probably do it with terrifying accuracy. Your brain is incredibly good at predicting the future, as long as the present is boring. The water flows at a constant rate, the glass has a constant width, so the water level rises at a constant speed. Easy. But what happens when we change the rules? Look at the water level now. It shoots up quickly at the bottom, but as the glass gets wider, the water level slows down. It's crawling near the top. If I asked you to close your eyes and predict when this glass overflows, it's much harder. But here is the crazy part. You can still do it. You don't need a ruler. You don't need a calculator. You can intuitively feel the relationship between the widening glass and the slowing water. You might not realize it, but in the few seconds it took to fill that glass, your brain just performed one of the most notoriously difficult operations in advanced mathematics. You didn't use numbers. You used intuition. Today, I want to show you why you are constantly doing integral calculus, even if you don't know it yet. Chapter 2: Stacking Dimensions. To understand what your brain just did with that glass of water, we have to go back to third grade. We have to talk about area. When you first learned about area, you were probably given a formula. Length times width. If a square is 4 inches wide and 4 inches tall, the area is 16 square inches. It is clean, it is simple, and it completely hides what is actually happening. Let's look at this differently. Imagine this square isn't a flat shape at all. Imagine it is made of lines. Think of a single line, a one-dimensional object. It has length, but it has absolutely zero width. By itself, it has no area. But what if we took that line and we swept it across the board? This is the true secret of area. A two-dimensional shape is just an infinite stack of one-dimensional lines. You take a line of a specific length and you add it up over a specific distance. Think of a ream of paper. One sheet of paper is practically two-dimensional. It's just a flat surface. But if you stack 500 of these perfectly identical flat surfaces on top of each other, you get a three-dimensional object. You get volume. We just upgraded dimensions by stacking. This act of stacking, of accumulating tiny slices to build a bigger whole, is the fundamental DNA of integral calculus. In fact, that terrifying symbol you see in calculus textbooks, the elongated S, it literally just stands for sum. It means add up all the slices. When you calculate the area of a square using integration, you are telling the universe to take a line of length 4 and stack it up along a tiny thickness we call dx. Chapter 3: The Secret of 1/2. But squares are boring. Stacking identical sheets of paper is easy because every sheet is exactly the same. The real world doesn't work like that. The real world is messy. The real world is a triangle. This is where our intuition usually hits a brick wall. We know the formula for the area of a triangle. It is 1/2 base times height. But where does that 1/2 come from? Why does the universe demand we cut it in half? Let's use our new superpower. Let's look at the triangle not as a shape, but as a stack of lines. If we start at the tip of the triangle, our first line slice is basically 0. It is tiny. But as we move to the right, sweeping across the shape, something changes. The slices aren't identical anymore. They are growing. Every time we add a new slice to our sum, it is slightly larger than the one before it. If I try to build a triangle using thick, chunky slices, it looks like a staircase. It's a terrible approximation of a triangle. The edges are jagged. You can visually see the missing gaps of area. If I make the slices thinner, like playing cards, the slope gets smoother. The approximation of the area gets better. Calculus is simply asking the question, what happens if the cards become infinitely thin? What if the width of our slice, our dx, becomes so small it is virtually 0? When the slices become infinitely thin, the jagged edges disappear. You get a perfect, smooth line. You get the area of the triangle. And this is where the magic happens. Because our line is growing at a constant rate, when we add up all those infinitely growing slices, the mathematics spits out a beautiful little fraction. 1/2. That formula you memorized in middle school. It's not just a rule, it is the mathematical footprint of a growing line. Chapter 4: The Martini Glass Paradox. Okay, so what does stacking growing lines have to do with pouring water into a martini glass? Look at the cross-section of a highball glass. It is a rectangle. When we pour water in, we are stacking identical disks of water on top of each other. The area of the surface never changes. It's just like stacking identical sheets of printer paper to make a square. Because the slices never change, the water rises at a perfectly constant speed. Now look at the martini glass. From the side, a martini glass is just a triangle spun around in a circle. When the water starts at the bottom, the surface area, the slice of water we are adding, is tiny, just like the tip of our triangle. Because the slice is so small, a little bit of water makes the level rise incredibly fast. But as the glass fills, the triangle gets wider. The slices are growing. Now, every second you pour, the water has to spread out over a much larger surface area. You are trying to fill a larger and larger slice with the same amount of water. So the water level slows down. It has to. And what if the glass isn't a straight triangle, but a curved wine glass? The surface area doesn't just grow linearly, it curves outward exponentially. The water level decelerates even faster along a curve. And your brain knows this. When you watch that water pour, your eyes track the widening glass. Your visual cortex measures the growing width of the slices, and your brain instantly calculates the slowing rate of the rising water. You are taking the physical geometry of a triangle or curve, processing the changing rate of a growing slice, and predicting a future outcome. You didn't write down the integral of x dx, but your brain computed the exact same logic. You intuitively performed integration. Chapter 5: Dashboards and Kinematics. Once you realize that integration is just the mathematics of accumulating slices, you start seeing it everywhere. It is not just geometry. It is time. It is motion. Think about driving a car. When you look at your dashboard, you are looking at two different dimensions of reality. Your speedometer tells you your speed right now, in this exact frozen millimeter of time. It is a one-dimensional slice. Your odometer tells you the total distance you have traveled. The area, the accumulation. If you drive at a constant speed of 60 miles per hour for 2 hours, calculating the distance is easy. 60 times 2 is 120 miles. It is a rectangle. You stacked 120 identical hour-long slices. But driving is never constant. You accelerate, you brake. Your speed is a wavy, chaotic line. How does the car know how far you have gone? It slices time. The car's computer looks at your speed for one tiny fraction of a second. A DT, it calculates the microscopic distance you traveled in that millisecond. Then it looks at the next millisecond. And the next. It adds up an infinite number of changing slices to find the total area under that chaotic curve. The car is integrating your speed to give you your distance. And again, you do this too. If you run to catch a bus, and you speed up and slow down to dodge pedestrians, your brain is constantly updating your distance to the bus. You are integrating your own changing velocity in real time to make sure your hand hits the door before it closes. Chapter 6: The Math Already Inside You. We are taught mathematics as a system of strict rules. We memorize formulas for squares, and triangles and parabolas, and we take tests, and we get grades, and most of us decide that math is a rigid, cold language spoken only by computers and engineers. But that is backwards. Math was not invented to torture you. It was invented to describe the intuition you already possess. When Isaac Newton and Gottfried Leibniz were developing calculus in the 17th century, they were not trying to make life harder. They were trying to build a language that could keep up with the physical world. The world does not move in static rectangles. The world grows. It accelerates. It flows. To understand a flowing world, you have to be able to chop it up into infinitely small, frozen slices, understand what is happening in that exact microscopic moment, and then glue it all back together. That is all integration is. It is the realization that complex things are just an infinite accumulation of simple things. A triangle is just an infinite stack of growing lines. A total distance is just an infinite stack of fleeting speeds. The next time you fill a glass of water, or step on the gas pedal, or catch a falling set of keys, take a second to appreciate what is happening inside your head. You don't need a chalkboard to do calculus. You just need to exist in the world. The math is already inside you. You have been solving integrals your whole life. You just didn't know the name for it.